So the last new proof method that I want to showcase is a uniqueness proof. And this is where you want to show that something is unique, of course. And usually the idea is to take two such things and show they are equal. So for example, now this example, I hope I'm not going too far for anyone to follow. I just want to not, I feel like being a number theorist, I really enjoy all the number theoretic stuff. And so does the textbook, like it's a good source of these examples. But I want to give an analytic example for anyone who's interested in analysis. So don't worry if you're not familiar with differential equations. You don't really need to know differential equations. Don't really need to know calculus even. I just want to, at least hopefully you'll understand the outline. But if you know a little bit of calculus, that'll be enough to understand what's going on. So consider the initial value problem. Dy dx equals e to the x squared and y of 0 equals 1. Okay, this is just some differential equation. I don't actually know how to solve it. It's just, doesn't really matter what it is. It's just something. And the claim is, if a solution exists, it is unique. So let's follow the idea that we outlined at the top. So we're going to take two solutions and show that they're equal to each other. So let y1 of x and y2 of x be two solutions. So what do we know about a solution to this differential equation? Well, we know its derivative, and we know its value at 0. So we're going to have to use these two things to show that they're equal. And here is another common idea that you might see, especially in these analytic kind of situations, is that to show that two functions are equal, consider their difference and try to show the difference is 0. Because somehow it's like, the way theorems are written and the way you think about things, it's often easier to show a function is 0 than to show that two functions are the same. So consider z of x, which is y1 minus y2. And now what do we know about z of x? We know its derivative, and we know its initial value. So what is dz dx? It is dy1 dx minus dy2 dx. But we've assumed that y1 and y2 are solutions to the same initial value problem. So they have the same derivative, and this thing is 0. And here's a calculus fact that might not be totally obvious, but you may be familiar with. If you have a function whose derivative is 0, you can conclude that it is a constant. The only function whose derivative is 0 are the constant functions. Okay, so we've used one piece of information, which is the derivative. We haven't used the other piece yet, so let's try that. The other piece of information is the initial value. So what is z of 0? Well, again, it's equal to y1 of 0 minus y2 of 0. And again, since those are the same, that is equal to 0. So since we know z of x is a constant, and at 0 it is equal to 0, then we conclude that z of x is equal to 0 everywhere. And that's what we wanted to show, right? So this is how uniqueness proofs often go, is whatever different situation you're in, whatever information you have, you take two objects that satisfy the thing you want to show is unique, and then you use the information about that object to show that they have to be the same.